All right, moving on to the next AP question. For times t between 0 and 31, the rate of change of the number of mosquitoes on tropical island at time t days is modeled by r of t equals 5 radical t cosine of t over 5 mosquitoes per day. There are 1,000 mosquitoes on tropical island at time t equals 0. So that this last sentence here says at the beginning, at time t equals 0, there were 1,000 mosquitoes. But then the rate of change of mosquitoes varies based on this function r of t. So the rate of change of mosquitoes is given by 5 radical t cosine of t over 5. So the units, because this is a rate, are in mosquitoes per day. So even though this is called r of t, I've been given a derivative. I've been given a rate of change, the rate of change of mosquitoes. So now let's look at part A. Show that the number of mosquitoes is increasing at time t equals 6. So I want to show the number of mosquitoes is increasing. So what I would need to show is that the rate of change of the number of mosquitoes is positive. So here's where a lot of students are going to make a mistake, is they're going to think I need to take the derivative of r of t and substitute in 6. Because they understand that to find where a function is increasing, I need to know that its derivative is positive. So at this specific time, I would need to show that the derivative is positive. But this is a derivative. This is a rate of change. It's the rate of change of mosquitoes. So if we want to show that the number of mosquitoes is increasing, I need only plug 6 into r of t and show that r of 6 is positive. So for part A, I need to find r of 6 and show that this quantity or this value is positive. So now going to our graphing calculator, we're going to use this function often, so we're going to store it as y1. This whole problem is a graphing calculator problem. So I've stored it as 5 radical x cosine of x over 5. Again, making sure I'm in radian mode still. When you enter this function, just be careful that the square root function stops with just x underneath it, and then you move to the right and get out of the radical before you put cosine x over 5. So the biggest mistakes are going to happen just entering in the function incorrectly. So now that this function is stored, I need to find r of 6. Well, we just called that function y1. So on the home screen, I'm going to go to vars, yvars, enter, enter to get y1. So what I want is y1 of 6, because we stored r as y1. So this looks exactly like this does because we stored r as y1. So now we can just go ahead and hit enter, and we get out 4.4379, etc. So this is a positive quantity. So r prime of 6 equals 4.437, which is greater than 0. So the number of mosquitoes is increasing. I'll just abbreviate mosquitoes, is increasing. So here the big picture is we don't need to see the prime notation to understand this is a derivative. The fact that this is a rate of change, mosquitoes per day, so this just goes back to the very first topic, the beginning of the year, understanding a quantity versus a rate. So since when substituting in a time here, I get out a rate, mosquitoes per day, this represents a derivative. So it's the rate of change of mosquitoes. So if I want to know whether the number of mosquitoes is increasing at time 6, I need only plug 6 into the rate of change of mosquitoes, which is called r of t. Alright, part B. At time t equals 6, is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? Give a reason for your answer. Alright, so part B really pushes whether or not you understand, again, the concept of rates. So we just said that even though this has no prime notation, this r of t function is a derivative. It represents a rate of change with the units in mosquitoes per day. So substituting in 6, r of 6 was 4.437, but again, the units would be mosquitoes per day. So on day 6, the rate of change is 4.437 mosquitoes every day. Now, part B is asking, is the number of mosquitoes increasing at an increasing rate? So what that means is we're trying to figure out if from day to day the number of mosquitoes, the rate of change of the number of mosquitoes is on its way up or on its way down. So around 6. So on day 5 to day 7. On day 5 was the rate of change, let's say, less, and on day 7 was the rate of change more, so that the rate of change was on its way up, meaning that the rate of change was increasing at an increasing rate. Or maybe on day 6, the rate of change was 4.437, but on day 7, the rate of change was 2.437. So the rate of change is increasing. The number of mosquitoes on the island is still getting bigger, but it's getting bigger at a decreasing rate. So, in other words, from one day to the next, more mosquitoes are still going onto the island, but not as quickly. So either the number of mosquitoes we're adding is going up every day, or the number of mosquitoes we're adding is going down every day. That's the question we're asking. So in order to determine that, we are now going to need the derivative of the derivative. So we are going to need r prime of t's sign, whether that is positive or negative. So for part B, I'm interested in r prime of 6. That's a rate of change of a rate of change. So r prime of 6 is truly a second derivative. So to find r prime of 6, I can go back to my calculator. I still have it stored r as y1. So now I need a derivative. So math 8. And I have d dx of the stored function y1. And I want that evaluated at 6. So since this is a negative quantity, r prime of 6 is negative 1.913, which is less than 0. So the number of mosquitoes is increasing at a decreasing rate. So every day, more mosquitoes are going to be on the island, but the number of mosquitoes added every day is going to be less and less. So on day 7, maybe 4.2 mosquitoes are added, and then on day 8, 4.3 mosquitoes are added. So it's specifically, though, at time t equals 6. So we're interested in what's going on right at this time. So that's why we needed to calculate r prime of 6. So the answer is increasing at a decreasing rate. And that's the reason for my answer. So there's no explanation. The reason is the notation that we wrote down, that r prime of 6 is negative 1.913, which is less than 0. All right, moving on to part C. According to the model, how many mosquitoes will be on the island at time t equals 31? So after the 31st day, how many mosquitoes will be on the island? Round your answer to the nearest whole number. Alright, so here on this problem, we are going to need to take into account 1,000 mosquitoes, which is how many were on the island to begin with at time 0. So for part C, how many mosquitoes were on the island after 31 days? So 1,000 is where we were to begin with. And now r of t is the rate of change of the number of mosquitoes at different times t. So I'm going to need to integrate this quantity. So I'm going to add the integral of the rate of change between 0 and 31 days. So between t equals 0 and t equals 31 of r of t dt, this is the net change in the number of mosquitoes. So this is the total net changes in how many were added, how many were subtracted over the whole course of 0 to 31 days. So this is the total net change plus how many there were to begin with. So now this can be evaluated in my graphing calculator. And again, if you don't understand why just outright this represents the net change in the number of mosquitoes, we can always go back to units. So again, just graphing. R of t is some generic function where the units of r of t are the rate mosquitoes per day. After so many days, t, the area again, the units would cancel. Area is base times height. So mosquitoes per day times days. The units of days cancel to give us just mosquitoes. And my answer, or my question, was asking for how many mosquitoes. So we're plugging this into our calculator. R of t has been stored for a while now, so we're going to do, and if we want, we could jump straight to 1,000. Whoops, let's do that. So let's say 1,000 plus, and then math 9, the integral from 0 to 31, and then our function is y1, and the variable is x. So this up here means it's taking a little bit of time to compute. So our answer is 964. So let's go ahead and write that down as our answer. And again, we were allowed to round our answer to the nearest whole number because there's no such thing as, 1/3-ish of a mosquito. So we could just say 964 mosquitoes is our answer. So it turns out that over the 31 days, the rate of change of the number of mosquitoes told us that a lot of them were dying out, right? So we started out at 1,000 and we added the net change in the number and we lost 36. So that's what happened during the time frame from 0 to 31 days. And finally, part D. To the nearest whole number, what is the maximum number of mosquitoes for times t between 0 days and 31 days? Show the analysis that leads to your conclusion. So trying to figure out what was the maximum number of mosquitoes at a particular time on the island. What was the most amount there ever was? So we know how many mosquitoes there were on the island at time 0 to begin with. So this is a closed interval, so I would need to determine how many there were at time 0. Now here's the biggest mistake students are going to make is they're going to say that we're trying to maximize R. So they're going to say, well, we want R of 0, we want R of 31, and then any critical points. So set this R equal to 0 to find the critical points. But that's not the case. We're not trying to maximize R. So I'm going to erase this because this is completely wrong. So we're not trying to maximize R. R is the rate of change of mosquitoes per day. I want to maximize the mosquitoes per day. So I don't have the name of that function. So we're used to using that notation. We want to maximize f, so we set f prime equal to 0, etc. But we don't need that notation in order to figure out all the important days that we're going to need to check. So all we need to do is say that at t equals 0 days, there was 1,000 mosquitoes. And we even have how many mosquitoes there were at 31 days. We solved that in part C. So at 31 days, there was 964 mosquitoes. So right now, just checking the endpoints, we know that, or we could say that the current maximum would be 1,000 mosquitoes. But we need to check any critical points. So we need to check critical points by setting the derivative equal to 0. And again, for the who knows how many times, this is the derivative of the function that counts mosquitoes. So we don't know what that function is. We don't have a name for it. But the derivative of that function that counts the number of mosquitoes, the rate of change of the number of mosquitoes, is R of t. So I need to set this derivative equal to 0. So how we're going to do that, because we have a graphing calculator, so ultimately this is what we're trying to do, figure out when does R of t equal 0, between 0 and 31, we're going to graph it. And we already have it stored, so here's our y1. And before we graph it though, I'm going to go ahead and modify the window. So x min, so x in this case represented our t. And we only care about what's going on between t's between 0 and 31. So our x min will change to 0, and our x max will change to 31. Alright, so now our y min. So y being the output. So here, let's just go ahead and leave -10 to 10, because we're not entirely sure what this function maybe is necessarily going to look like. I mean, it has the cosine function in it. Just cosine itself goes from -1 to 1, but just to see, let's go ahead and and graph this function. Alright, so we have a pretty good picture. We don't have the entire picture, but we do have where r of t equals 0 clearly shown. So there's two places where this function r of t equals 0, this derivative equals 0. So we have two critical points right about here and right about here. Now, normally we would have to check both critical points, but we are trying to find the maximum number. So I would say that the best thing to do is to eliminate any local minimum value, because that's not potentially ever going to be a maximum. So here this derivative graph changes from positive to negative, so that means the original function goes from increasing to decreasing, so this point here would be a local max. This is the one we want to keep and we care about. This other function, or this other critical point, is going to yield a local minimum, because this derivative graph changes from negative to positive, making the function change from decreasing to increasing, the original function, which means there'd be a local minimum. So we do not have to care about this point, only this one. Alright, so now I have to find this 0. So to review how to find zeros on our calculator exactly, because let me point one thing out. The trace option doesn't work. So here's what I absolutely cannot do, is just move my arrow over and get kind of close to that point and say, oh, that's the x value that I need. I absolutely cannot do that and will never ever work. So I have to go to second trace for calculate, 2 for 0, and now it's asking me for the left bound. So I want to be to the left side of this x-intercept right here. So I want to move to the left. So now I'm clearly to the left of this x-intercept. So I don't want to think about it as above or below the graph, the x-axis. I want to think about it to the left or to the right. So left bound, yes, so I hit enter. Right bound, now it's telling me get to the right side, which in this case would be down here. I'm on the right side of this x-intercept, so I hit enter. When it says guess, we always just hit enter. So now we have that this 0 is 7.85398, etc. Alright, so if we want to remember that value, we could go ahead and write it down. So 7.853. So let's just write it down so we remember it. But here is something that is crucial. I cannot just take this value, even if you go out to 25 decimal places or 25 places past the decimal, I cannot just take this numerical value and type it in right now when we set up our integral. I have to store this value. So right now the calculator is holding this number as your last answer. So what we're going to do, as soon as you see this value as the 0, I'm going to go to second and quit. I'm going to get to the home screen. And the first thing I'm going to do, I can't touch anything else, I have to hit STO for store. So what the calculator is doing is it's storing your last answer, which was, they're only saving the x coordinate. So the last answer, I want to store it to any letter in my calculator except x. I don't ever want to do that. But I want to store it to, let's say, A. So alpha A. So I'm using the green buttons on the back. If you have a different color calculator, it might be a different color. So alpha and then any letter you want. Usually we pick A, it's closest, and then we hit enter. And then we wrote it down so we remember. A is now 7.853, and it's the exact answer with all of the decimal places stored. So now I want to keep and hold that number. So that answer is in terms of days. Whoops, days. So potentially the maximum number of mosquitoes happens at 7.853 days. The only way we're going to know is to evaluate the integral from 0 to A. So what I'm going to do is, instead of calling this t now, I have labeled it as A. And on the AP exam, you're going to want to do this as well. So you're going to want to list what you stored as A, and then the integral we're setting up to find the number of mosquitoes there were at 7.853 days is the integral from 0 to A of r of t dt. So now we're going to go to Math 9, for integrals. 0 to my upper limit of integration is now a. So under no circumstances can you type in just 7.853 or even 7.853 blah 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 1020 places past the decimal. You have to put the stored value in. And then we can go ahead and choose the function y1 again, and then dx, and enter. And this number is going to represent the net change in the number of mosquitoes between 0 and 7.853 days. So this is the net change in mosquitoes between 0 and 31 days. So we can't forget to add, didn't leave much space for it, but we can't forget to add 1,000 to that net change. So that's how many mosquitoes were added to the island between 0 and 7.853 days. But there were already 1,000 to begin with, and our question's asking what's the maximum number there were. So the answer here is 1,039 mosquitoes. So the nearest whole number, we're rounding again, and that would be the maximum. So what is the maximum number of mosquitoes? 1,039 mosquitoes. And now to the final AP question we're going to take a look at. A tank contains 125 gallons of heating oil at time t equals 0. During the time interval t between 0 and 12 hours, heating oil is pumped into the tank at the rate of h of t equals 2 plus 10 over 1 plus natural log of t plus 1 gallons per hour. And during the same time interval, heating oil is removed from the tank at the rate of r of t. So 12 sine of t squared over 47 gallons per hour. So before we look at the parts of the question, let's make sure we understand what's happening. We have this tank that starts out with, at time 0, 125 gallons of heating oil. And between 0 and 12 hours, oil is pumping into the tank at this rate here in gallons per hour. But during the same time interval, heating oil is also being removed from the tank at this rate of 12 sine of t squared over 47 gallons per hour. So this is a calculator problem, and we're first going to enter in each of these functions as y1 and y2. So we'll go ahead and enter 2 plus. Now when I have a rational function like this, I want to make sure and enter the numerator and denominator in their own set of parentheses, especially if I don't have this updated calculator. If you have the updated calculator, we could always go to alpha and then y equals and choose 1 for numerator over denominator, and then just enter in the rational or the function exactly as it looks. So we have 1 plus natural log of 1 plus t, or t x in this case. The order doesn't matter there. So I entered 1 plus x, that's the same as x plus 1. And then we'll go ahead and enter in our second function. So that one is 12 sine of the quantity. So we have t squared, so x squared, get out of the exponent, and then divide by 47. Alright, so we want to make sure we've entered in our functions correctly, because we're just going to now use the stored versions of y1 and y2 every time. We also want to keep straight the order that we entered them in. So because h of t came first, that one's y1, and I want to remember that, and then r of t is y2. Alright, so now that those are stored, let's go back and answer the questions. So for part A, how many gallons of heating oil are pumped into the tank during the time interval from 0 to 12 hours? So in this part of the problem, we're asked to find how many gallons. So I have my functions in gallons per hour. So I know I'm going to have to integrate these functions in order for the units to cancel out. We've done that a few times now. The units of hours will need to cancel, and then we'll have our answer in gallons. So we know we're going to need to do some integrating here. So we're going to need to integrate the function that involves pumping water into the tank. So how many gallons are pumped into the tank? So that was h of t between 0 and 12. So the integral I'm setting up is the integral from time 0 to time 12 of h of t dt. So it's just how many gallons were pumped into the tank, not how many gallons are in there total, so we don't have to care how many there were to begin with. It's just how many were pumped into the tank between 0 and 12 hours. So now h of t was stored as y1, so in case we might tend to forget, we can always label them as well. So they're stored for us. We can go to the home screen. We can go to Math 9 to set up our integral from 0 to 12, 12, of h of t, which we stored as y1. So vars, y vars, enter, enter, dx. And the answer is then 70. And because we were not told to round, we would always go to at least the thousandths place. So either round or truncate. So I'm going to write 570. And I also write the other answer that would be accepted on the AP exam, 70.571. So rounding the 10 thousandths place over 1 because that value was bigger than 5. So we would get 571 thousandths or 570 thousandths. So these two would be the acceptable answer for part A. Now, you cannot just write the numerical answer for my test or for the AP exam. The points are for the setup, for the limits of integration, for the integrand. Now, you don't actually have to go through the process of writing out h of t, which has already been given to us. You can just go ahead and call it by the name it was given, h of t. So there would be a point here for the limits of integration, a point for the integrand, and a point for the numerical answer. But just putting the numerical answer doesn't get you anything. So now, for part B, is the level of heating oil in the tank rising or falling at time t equals 6 hours? Give a reason for your answer. Alright, so we have this tank that's filled with oil, so we don't know the shape, but let's just say it's like a cylindrical tank. It has 125 to begin with. So at time 6, we're trying to figure out, is the level of the heating oil rising or falling? So the level has a measurement, let's call it H. So we want to know if more oil is coming in than is falling out. So if more oil is coming in at 6 hours, then is coming out right at 6 hours, then the level would be rising, the level of the oil. But if more oil is falling out right at 6 hours than is coming in, then the level of oil would be falling. So we're comparing rates here, the rate at which oil is coming in and the rate at which oil is coming out. Which one's sort of winning the race? So here we're comparing H of 6 and R of 6. So H of 6, the rate at which oil is coming in, is a value we can find on our calculator exactly. So H was Y1, so Y bars. Y1 of 6 is 5.394. So 5.394. So this is in gallons per hour. So this is the rate at 6 hours at which oil is coming in. So now let's compare that to R of 6. So that would be vars, Y vars. We can go down one to Y2 of 6. So the rate of oil coming out is bigger. It's 8.318 gallons per hour. So since more oil is coming out than is going in, the level of heating oil must be falling. So a reason for my answer is because R of 6 is greater than H of 6. The oil level is falling. And that's all we would need to state. So this portion here is our justification because 8 is more gallons per hour coming out than 5, which is the gallons per hour that are coming in right at 6 hours. Moving on to part C. How many gallons of heating oil are in the tank at time t equals 12 hours? So at 12 hours, how many total gallons are in the tank? So this is where we're going to have to take into account how many there were to begin with. So at time 0 to begin with, there were 125 gallons. So 125 plus, well, I need to figure out how many entered between 0 and 12 hours. So how many entered is going to be the integral from 0 to 12 of h of t dt. And that answer was also found in part A. So how many gallons of heating oil are pumped into the tank between 0 and 12 hours? That answer was found in part A. So how many total gallons are in the tank at 12 hours? Well, 125 was what we had to start with, plus this is my setup from part A. This is how many gallons entered during the 12-hour time frame, and I need to subtract how many left. So heating oil was removed based on the second function r of t. So between 0 and 12 hours of the r of t function will tell us the net change of how much oil came out between 0 and 12 hours. So what I had to begin with plus what went in minus what came out is going to give me the total amount of oil in the tank at time 12 hours. And it's going to take our calculator a bit of time to compute this, but I do want to enter this in as one giant expression. So I wouldn't want to find this answer or use my answer from part A and then calculate this and then subtract decimals and really ultimately get a worse off approximation. So in other words, I don't want to ever approximate intermediate steps, because if I were to truncate this at 3 decimal places and then truncate this at 3 decimal places and then go through the process of combining all of these, that's not going to give me as exact an answer as entering them all in at once. Alright, so I've entered in all of the values and I ended up with 122.025. So we could now round this final answer, so you'll see all of the integrals are entered there, as 122.025 or 122.026. Those would be the two acceptable answers. My units would be in gallons. So how many gallons were in the tank at 12 hours? So 122. So originally we had 125, so over the time frame it seems like definitely more came out than came in, because we ended up with less than we started out with. And finally, part D, and this is one of the trickiest parts of really any problem that involves this concept of one function that has something coming into an object and then another function that takes away. So this is going to be a little bit intensive on the graphing calculator and a little bit intensive to understand. So at what time t, for t between 0 and 12 hours, is the volume of heating oil in the tank the least? Show the analysis that leads to your conclusion. So I'm figuring out what time the volume, or really the quantity of heating oil in the tank, is the least possible amount. So I'm trying to minimize the volume of the heating oil. Now, right now, what I have in terms of functions is the rate of change of oil entering and the rate of change of oil leaving. So I don't have a function right now that represents the total amount of oil in the tank at any particular time. But I'm pretty much going to have to write one. So I'm going to call that function v of t, so for the volume of oil in the tank. And I'm going to, once I write this volume function, I'm going to try to minimize it. I'm going to try to find the absolute minimum value, the least quantity, between 0 and 12 hours. So the volume at any particular time, and hopefully this will seem familiar after you've done it enough times, the only thing that changes in these problems is what's coming in and what's going out. So the total volume is 125 gallons, what you had to begin with, plus the integral from 0 to some generic time t of h, and I can't call it t again, so let's say h of x dx. So let's stop and think about this. It's what we had to begin with plus how much is going in between 0 and t minus how much is going out between 0 and t. So we'll have to say that that is now r of x dx. So this function v is now representative of the total amount of heating oil in the tank at any time t. So the units of this function are in gallons. And in order to find the minimum, we're going to need to check the endpoints and the critical points. So the endpoints are 0 and 12. So we need v of 0, the amount of oil in the tank at time 0. We're going to need v of 12. Well, thankfully, we have those values. At time 0, there was 125 gallons. At time 12, we just did that in part C. So that was 122 gallons. 122.025 gallons. So now it's a matter of finding critical points, which means taking the derivative of this volume function that we're trying to minimize. So we need v prime of t. So the derivative of 125 is 0. The derivative of this integral with an upper limit of integration of t, so we're taking ddt of the integral from 0 to t, which is just taking this t and substituting it into this x. So v prime of t is h of t. And then taking the derivative of this function here, again, same thing. T goes into the x. I'm taking the derivative with respect to t. This is an accumulation function. This is an application of the FTC part 2. So minus r of t. So what I want is where the derivative equals 0. So I need to know, when does h of t minus r of t equal 0? So now let me remind you that we stored h of t as y1 and r of t as y2. So what this amounts to is, when does y1 minus y2 equal 0? Well, there's kind of a cool thing we can do on our calculator. We can, since we have already stored y1 and y2, we can go down to y3, and while we absolutely could retype out this function, h of t, and this function, which was r of t, what would make it even quicker is if we just entered y1 minus y2 as y3. So now y3 is y1 minus y2. But when I graph this right now, I don't want to see y1 and y2. I don't want to delete them. I can't delete them because y3 is referencing y1 and y2. But what we're going to do is hover over the equal sign and hit enter to turn it off. And all that means is I don't want to see it when I graph right now. It doesn't mean I want to get rid of it altogether. So again, don't delete y1 and y2, just turn them off. And we're going to change our window from 0 to 12. So that those are our t values that we care about here. And we can leave our ymin, ymax for now until we potentially have to change it. So this function that's being graphed can be thought of as v prime of t. Now remember, we're trying to find the least amount. So we're trying to find a minimum. So on this graph, this is a derivative. If the derivative changes from positive to negative, the original function goes from increasing to decreasing. That's a maximum. So in other words, I do not care about this critical point right here. I do, however, care about this one because the derivative that is graphed is changing from negative to positive, so this is a minimum. Alright, so I skipped showing finding the 0 on my calculator, the process that we did earlier. So I found the 0 of this critical value that I care about, and the 0 was 11.318. So I do want to write that value down before I store it. So I'm going to go ahead and just write in the corner A, because that's what I'm going to store it as, is 11.318. So now let's remember, we go to second quit immediately, hit store immediately, and then choose a letter. So if I choose A, I have to know I'm rewriting over the other A that I stored. So now A is this 11.318 value. So that's the critical point. So now the other quantity that I need is V of A. I'll go ahead and call it. Since I wrote A over here, I can just write A as what I'm evaluating the function v as. So v of a is 125 plus the integral from 0 to a of h of t dt minus the integral from 0 to a of r of t dt. Sorry, we ran out of space there. But how we calculate this is how we calculated the time 12 hours in part C. We enter the whole thing into the graphing calculator all at once. Just to show you another kind of cool thing we can do, these two integrals, by our properties of definite integrals, can be thought of as the integral from 0 to a of h of t minus r of t. Well, we called that in our calculator y3. So I'm saying that so that right now when I enter in my integral, it'll be a little bit faster to say plus, and then math 9, the integral from 0 to a of y vars and then y3. So y3 was y2 or y1 minus y2. So I can do that instead. Which is going to take the calculator just a couple seconds longer because now it has to reference some other functions, but definitely not too long. So that means that 120.738 is my answer to v of a. So the minimum value, that's right, 120.738, doesn't look like a 3, 738, is the smallest. So at what time t is the volume of heating oil in the tank the least? Show the analysis. This is showing the analysis, checking v of 0, v of 12, and v of a, and you are going to have to specify what a was and that you checked it, because in fact that a ends up being the answer. So at what time t? At time 11.318, what were my units? Hours. This is the minimum. So this is the justification, and ultimately this is my answer. So sorry we kind of ran out of space on that last one. But part D typically does have the most amount of work and is the most challenging. What I will leave you with is that hopefully you started to see some of the patterns in these problems. They are not always going to be identical. They're not going to have the same structure. They are going to require you to definitely understand what a rate is, understand the concept of units, what happens when we take the derivative, what happens when we take the integral, what happens when we just substitute in values into the functions that we're given. There's a lot of conceptual understanding here. And there's also a lot of applications to the graphing calculator. So we've definitely gone through a roller coaster with not being able to use our calculator at all for a big portion of this class, but now you need it, and you need to know the ins and outs of your calculator. It's not optional to not know how to store these functions, not know how to find zeros, store the limits of integration. You have to know how to do this to be able to get these questions correct on the test that's coming up. So if you have a different calculator and you want to work one-on-one with it, you're going to have to come in long before the test to get help with it, because it is something that requires some practice and some getting used to, and you don't want your calculator to get stuck on you during the test, or I can't answer those questions during the test. I can't tell you how to clear it or how to clear the memory, or if it's in radian mode or degree mode and your answers are all incorrect. Those are things you have to figure out long before you take the test. So hopefully you definitely got to the end of this video, because this part D is the most important one, especially that it has two functions associated with it. So you will absolutely see this type of problem all over the assessments that you'll take going into the near future.